In this video, I want to look at how we prove a sequence converges. This is one of the most important skills to learn in real analysis because proving sequences converge is an important part of many of the proofs that we will be looking at later on in the semester. To get started, I want to look at this example. You should stop the video, copy the problem over in your notes carefully, and then start the video back up to see how I approach this problem. What I want to notice is that in this particular problem, we have a piecewise defined sequence, and we're being asked to determine whether or not the sequence converges, and if it converges, what it converges to, and we're being asked to prove that our answer is correct. So to get started, this is how I would approach the problem. The first thing that I would do is I would simply list some terms from the start of the sequence. In other words, get a feel for what's going on. So the start of this sequence looks like this. It starts with 1, and then we have 1/2, and then we have 10/9, and then we have 3/4, and then we have 26/25, and then we have 5/6, and then we're going to have 50/49, and then we will have 7/8, followed by 82/81, followed by 9/10. And that's enough terms for me to get a good idea about what's going on. It also helps to sometimes graph these terms on a number line. So when I come back and I start graphing them, here's 0, here's 1, here's 2. I'm going to basically just plot these points in, I don't know, let's try this color. P1 is 2. P2 is down here at 1/2. P3 is back up on this side, but closer to 1 than P1 was. P4 is here. P5 is closer to 1 than P3. And P6 would be here. It looks like we're alternating back and forth, hopping back and forth across the line x is equal to 1. So in looking at the numbers that I'm getting at the start of this sequence, I can make the conjecture that my sequence appears to converge to 1. We will prove this starting with the next page. So we need to prove that our sequence of pKs actually converges to 1. Now here's how we have to do it, and let's actually put the proof in yet another color. So the proof. We have to start with an arbitrary open interval. So we want to say let S be an arbitrary open interval containing x. Well, actually containing 1, because our limiting value here is 1. Now, what I want to do is I want to kind of think in terms of a number line over here. So there's my number line, here is 1, and here's this open interval. And I don't care if it's a balanced interval or not. The next thing that I want to do is I want to pick a delta bigger than 0 that is so small that the delta ball centered at 1 is a subset of S. So I'm going to put that delta ball in a different color. So there's my delta ball. and it is centered at 1. And my goal is to find an entail that is trapped inside this delta ball. Now, what I want to think about is, what does that mean? To trap the tail inside that delta ball, what I want is to find a capital N such that the distance between Pn and 1 is less than delta. And I know that that's what I'm wanting to do, because what I'm wanting is Pn to be somewhere inside this delta ball. I don't care which side of 1 that Pn is on. Now, this is going to come back in just a minute, but it's important to understand that Pn is inside the delta ball if its distance between it and 1 is less than delta. This particular thing here is what tells me that Pn will be inside my delta ball, and my delta ball, of course, is a subset of the original open interval. Now, the only thing is I want to make the note that if Pn, well, actually, I want to say it this way. If n is odd, then what I know is that Pn, which is n squared plus 1 over n squared, is actually bigger than 1. And if n is even, Pn is equal to n minus 1 over n, and that is less than 1. So what I want to do is I want to pick up on this fact on the next page. So here's my number line. And I'm going to kind of blow the number line up so that we can see exactly what's going on. Here is 1. Here is my delta ball. So this is 1 plus delta, and this is 1 minus delta. Now, what I know is that if n is odd, Pn lives up here. And so if n is odd, the distance between Pn and 1 is nothing more than Pn minus 1, and that's going to be n squared plus 1 over n squared minus 1. And it turns out that that's going to be 1 over n squared. On the other hand, if n is even, Pn is over here. And so I want to make that note. And in this case, the distance between Pn and 1 is going to be 1 minus Pn, and that would be 1 minus n minus 1 over n, and it turns out that that winds up being 1 over n. Now, what I want to do next is I want to remind you about one thing. I want to remind you that 1 over n squared is always less than 1 over n for all natural numbers. So over here, this is always going to be less than 1 over n. So when n is equal to odd, so when n is an odd number, this distance that we need to be small is still going to be less than 1 over n. So putting these two facts here together, we have, for all of our natural numbers, the distance between Pn and 1 is less than or equal to 1 over n. Now, this is going to be something that I want you to remember because it's going to come back on the next page. We also want to recall an important theorem from chapter 2. Theorem 24 says, if I have a tiny little number delta, there is always a capital N inside the natural numbers, such that 1 over capital N is less than delta but bigger than 0. And that's all I need to finish this proof off. We have already been given a delta bigger than 0, so we find a capital N such that 1 over n is less than that delta. Then I make the claim that the entail of my series, the entail of my sequence, is indeed inside the appropriate delta ball. And here's the proof of the claim. So here's why. We've already seen if n is bigger than or equal to capital N, that the distance between Pn and 1 is less than or equal to 1 over n, and that is less than or equal to 1 over capital N, and 1 over capital N is smaller than delta. And that says Pn is inside my delta ball whenever little n is bigger than or equal to capital N. And that says the whole entail of the sequence is indeed a subset of that delta ball, and that delta ball is indeed a subset of our original arbitrary open interval. And therefore, by the definition of convergence, my sequence does indeed converge to 1.